Started? Yeah. I'm going to whiz through infrared and mass spec. Of course, you've done infrared and mass spec before, but just with a little bit more focus. So the idea of infrared is that you take a beam of infrared light and then you pass it into a splitter, splits the light into two equal paths, and then you pass one beam of light through your sample and the other beam of light through control, which is basically the same. You put the samples between little cells, so you have a couple of little cells for the control but no sample between them, and then you bring them back together and feed the information into a computer. Still looks like that in my world. And it gives you a spectrum. What it does is just literally compares the two sets of data, and then we get a spectrum. So the spectrum appears as what is it called? Transmittance, which is an odd word to use. It's about how much of the light is transmitted. So if 100% of the light goes through the sample, it'll be up at the top. The spectrum will be up at the top. If the sample absorbs all of the light, or some of the light, then you get a big dip. Now we call the dip a peak, even though really peaks are the other way up, aren't they? Peaks usually go, the peak of a mountain is usually above you, not below you. But despite that, we call them peaks. Now the frequency of the light comes out in a rather awkward unit called the wave number, which is the unit is centimeters to the -1. You don't really need to worry about this, but if you are worried about it, then remember that frequency is proportional to 1 over wavelength. So if you measure your wavelength in centimeters, then 1 over wavelength, centimeters to the -1, is the frequency of the light. So it's basically a frequency scale, but with an odd unit. That's the way I think about it. So the infrared light goes through the thing and we get a whole sort of mess of peaks. Looks like that. I should probably bring up a slightly better looking one from your topic booklet. There we go. Is that on? No, because we're on. Okay. So we get a spectrum that looks a bit like that. So we get a bunch of peaks. This, as it says, is the infrared spectra of propane. And if you're a first year degree level student, it's a fairly standard task to go through every single peak and label them all. You're not going to be asked to do that, but if you look on the internet, there's lots of examples of that. It's not what I want to find though. Should have lined this up in advance, shouldn't I? Okay, great. What's going on? Well, as it shows here, the carbon-hydrogen bond tends to stretch. Now, when we draw bonds, we tend to draw them as kind of static. But actually what you're looking at is two particles which are essentially on a spring. They can move apart from each other and they can move closer to each other, and that sets up a vibration, and the vibration has a frequency which is in the infrared range. So if you shine infrared light of a particular frequency at a carbon-hydrogen bond, it'll get a little bit excited and start to stretch. And that's the frequency right there. Actually, if you look carefully, there's a whole bunch of peaks, because in propane, there's a whole bunch of carbon hydrogens. So they're all stretching at slightly different frequencies, which is why you get a sort of bundle of peaks. And for any organic compound, you're always going to get that bundle of peaks, and it's around about 3,000 centimeters to the -1. So you're always going to see that. It's a little bit more complicated than that, though, because atoms don't just stretch. Well, they symmetrically stretch and asymmetrically stretch. They also rock and scissor and wag. Wag is where they're kind of doing this, which is me on camera doing that. And then there's that as well. If you hadn't done your yoga this morning, do some twisting and so on. So there's all sorts of movements that are going on, and they're going on all the time, but we only notice them during infrared spectroscopy. Okay, so propane's a pretty simple substance. It's got some carbon-carbon bonds and some carbon-hydrogen bonds. That's it. Some of those bonds are going to be absorbing infrared light down there, but to be honest, below 1500, so sort of around about here, below 1500 centimeters to the -1, we call that the fingerprint region, because we'll often get a specific pattern of peaks for a specific compound. So rather than going to the laborious work of finding every single peak, we can simply look it up in a database and it'll recognize that pattern and say, yeah, that's propane. So in other words, using it as a standard fingerprint. So there's just a few functional groups you should really be able to spot pretty much instantly as soon as you look at an infrared spectrum. The carbon-oxygen double bond. Now, of course, you've got the thingo. Is it on the inside of your booklet? Yeah. So you've got the list of infrared absorptions on the inside of your booklet there, and carbon-oxygen double bond 1680 to 1750, and there it is. But in addition to that, you should also be able to recognize the shape. So the carbonyl, carbon-oxygen double bond, is always a pretty sharp peak, and it's always good, strong absorption. In other words, it takes us almost right down to the line. So that makes it pretty easy to spot. The next one you should be able to spot is the OH group. But OH absorbs at different frequencies depending on if it's an alcohol, in which case it's right over to the left, or if it's a carboxylic acid, in which case it's further to the right. But as well as its position, notice its shape. OH is always a very broad, strong absorption, and being over to the left, it's an easy one to spot. These are the CHs just sticking out through the edge of the OH there, but OH is always the biggest peak on the spectrum. If I've got an OH acid, there we are, OH acid, so slightly to the right. Actually, the CHs have largely disappeared there. And there's the carbon-oxygen double bond. Of course, if you've got a carboxylic acid, you've got to have a carbonyl as well as the OH. So those are the main ones that you should be able to recognize. And most questions are about those. There are a few others. The for nitrile, for example. But if you were presented with this in an exam, you would simply look it up and go, okay, that's it. What is it at? I can't see the numbers. What's that? Just under 2300 CN 2260 to 2220 to 2260. So there we are. So that's bang in the right place, and there's nothing else that it could be in that spot. And there should be an alkene here as well. This is just from your topic booklet, by the way. Alkene, there it is, 1620 to 1680. That's pretty close to the carbonyl, but notice how different it is. The CC double bond is usually a smaller, sharper peak compared with that carbonyl, which is a really strong peak, again going all the way down to the line. Okay, and then that fingerprint region below about 1500, always a dense pattern of peaks that you're not expected to be able to identify there. Any questions about infrared? That's it. That's all I'm going to do on infrared. Bit on mass spec. Just literally a very little bit on mass spec. So in year 12, we tend to focus on elements when we look at mass spec, and we use the data to work out the relative atomic mass. For year 13, we're going to be much more focused on compounds. So this is the mass spec of ethanol, and I'm not going to go into the whole story about how mass spectrometry works, but you know, right, that if it's electrospray ionization, they dissolve it in a volatile solvent and spray it through a hypodermic needle with a high voltage, and it gains a proton, and that gives it a charge, so it can be accelerated through charge plates, and then it will travel down through a sort of time of flight zone where it's the speed that it's going at, the kinetic energy that it has, that determines, sorry, not the kinetic energy that it has, the velocity it has. They all have the same kinetic energy, of course, you knew that. The velocity that it's going that determines the thing. Anyway, you knew all of that. And if you didn't, you're going to do something about it. So if you put a molecule into a mass spec machine, there's a couple of important bits of information come out of it. Usually the most important bits of information is the largest peak, what we call the molecular ion. Oh, thanks. Remember, everything in a mass spectrum that's discovered is a positive ion. So the molecular ion, in this case, this is ethanol, is there at 46. Now, just a little note, because it's a common exam question and it's a sort of nasty, evil exam question. Remember when I was talking about electrospray ionization, I said the substance gains a proton. Proton has a mass of 1, right? It's got a proton in it. So if you add a proton to ethanol, actually the molecular ion peak would be at 47. So for the purposes of simplicity, these spectra that are in the book and that we're going to look at are all made by the other form of ionization, which is the electron gun ionization, which fires high energy electrons at the molecule and knocks an electron off, forming a positively charged substance. But that is a common exam question. Okay, so we've got a molecular ion at 46, but as the molecule starts to move through that, down that time of flight, as it's travelling, it's an unstable charged particle. They tend to start to fall apart, fragment. So by the time it hits the detector, we've actually got a whole bunch of other different ions there. Let's just deal with the 45. So the 45 has a pretty high abundance. Why would ethanol produce a fragment with an abundance of 45? Sorry, not an abundance of 45, a mass of 45. Take your time. Thanks, Ed. It's just going to lose a hydrogen. Yeah. Now, in fact, if it is electron bombardment, because it's lost an electron, it'll be a positively charged radical, so it's a plus dot, and it'll fragment into two pieces, one of which is positively charged. Well, it must be that one because the M over Z is 45, and the other one will be a dot. So plus dot goes to plus and dot. Okay. Can you have a go at writing a fragmentation reaction for that peak there? The largest peak on the spectrum is at 31. Always start with the original molecule, by the way. What is 31? So a way of thinking about it is, rather than focusing on the bit, the 31, focus on the bit that's gone. Well, 31 from 46 is 15. I've lost a fragment with a mass of 15. Well, 15, when you're looking at ethanol, has to be CH3. So I've lost CH3, which means the CH2OH bit must be the other fragment. That must be the positively charged piece, because we get the fragment ion on the spectrum, which means the other piece must be a radical. Okay. And you can see that after the 31, you often get this pattern of little lines, which is where hydrogens are falling off. So it's lost CH3, and there it's lost another hydrogen, and then another hydrogen, and then another hydrogen, and so on. But just before we go, those with sharp eyes will have noticed that, 46 is the molecular ion peak. There's a very, very tiny peak at 47. How can we get a peak at 47 for a molecule with a formula mass of 46? Anyone else? Right? Josh knows?
Does it react with the free radical hydrogen to add a add one to the mass?
Right, so apart from electrospray ionization adding a proton at the beginning of the process, the particles don't get together usually. They fragment, they fall apart, they separate. They don't join up. because they're all positively charged, so they wouldn't attract one another. There's no attraction there. Think back to your year 12 work. What's year 12 all about? It's to do with different isotopes. So it's usually called the isotope peak because in every sample of organic substance you've got mostly carbon-12, but you'll have a little bit of carbon-13. You'll have a little bit of hydrogen-2, maybe a little bit of oxygen-17, or other isotopes will exist as well. So you will often see a tiny isotope peak just above the main peak. Now, of course, some elements have a disproportionately large amount of isotopes in, and the two that you should have studied are chlorine and bromine. So if I've got chlorine in a molecule, the molecular ion peak itself will have that chlorine in. So the molecular ion peak will have a peak and then another peak separated by 2, because I've got chlorine 35 and chlorine 37. And remember, they're in a 75% to 25% ratio. So I'm going to see that sort of 3-to-1 ratio of peaks that are separated by 2. So spotting that would tell me there's chlorine in this molecule. Does anyone know the signature pattern for bromine off the top of your heads? No? You don't know bromine's isotopes? I'm disappointed. Okay, so bromine has 2 isotopes, again separated by 2, so 79 and 81, but they're almost in a 50-50 ratio, just slightly less of the 51. So again, if I do a mass spec when there's a bromine in the compound, we'll get these sort of twin peaks side by side, right up at the top there. So M plus for the molecular ion, and M plus 2 for the molecular ion plus 2 for the isotope. Just one last question. What's the formula mass of this compound? Can work it out if you like. It's not a trick question. It's a little bit of a trick question. What's the formula mass of bromoethane? Hundred and 109. What peaks do I see on the spectrum? Well, I don't get 109. I get 108, and I get 110. When you look up the mass of an atom, of course, you're looking up its average mass. So we look up bromine on a periodic table, it'll say it's got a mass of 79.9. But actually, there's 2 isotopes, one's 79 and one's 81. And in a mass spectrum, they travel separately. So we'll see a molecular ion and then a molecular ion plus 2, neither of which has the same mass as the formula mass, because the formula mass is using an average value. You just have to be a little bit careful of that. Yeah. Okay, that's all I'm going to say about that. Okay, that's good. Sure.